Good morning. I am Dr. István Szintai. Let me show you the world in my eyes. Meanwhile the travel to the moon, we have time to think about the night side of the sphere. For a repeat, I show you the side view of the standard temperature model and the fast rotating model, and the front view of these models, and the back view of these models. And as you can see, the fast rotating model looks the same from all these three directions. So we can write up that the half of the irradiation is radiating out from the half of the surface. So this will be mathematically equal with the isotherm model. And as you can see, the nighttime radiation is going to be the same if the rotational index is above pi. So the isotherm model is the theoretical maximum of the nighttime radiation. With this knowledge, we can start to build up the slow rotating model. For a repeat, the sphere is on circular orbit around the star. The axis of rotation is perpendicular to the plane of the orbit. And as a little cheat, we count as the sphere would be radiated from infinite distance, although you know that this is not the truth. And from the definition of the rotational index, we can write up the subsolar temperature. And in the standard temperature model, the nighttime radiation is 0. And for the fast rotating model, the nighttime radiation is equal with this expression I show you on this plot. The question is, what is in between them? We are talking about a type of matter. So during the night, the expectation is that during the night the surface will be radiate, and because of the radiation the surface will cool themselves. But what is in between these values of the extremes? If we think that the radiation that is missing during the day, it can be radiated out during the night, then we can approximate, or we can write up an equation for the expectation of the nighttime radiation. In these situations, all of these temperatures will be keep balance with the same irradiation. Let's see that x-axis. What is the rotational index? It's a very strange axis because there's no meaning of the unity. If the rotational index is 2 or 3, there is no special meaning compared to 1.69. And this scale has a theoretical maximum and a theoretical minimum. And this scale does not contain any connection with other physical properties, especially time. If we think a big sphere of iron or a big non-transparent balloon, then you can imagine that for the same temperature situations, these two bodies will have to rotate with a different speed. So rotational index does not have a direct connection with time. Only we can say that from these two equations, if we know two values, we can count the other two values. So if a sphere have 312 degrees at the subsolar point and 255 as the nighttime radiation, then we can say that this sphere has the rotational index 2.53, and this sphere keeps balance with the radiation of 1361 watt per square meter. Again, So if two spheres rotates with the same speed of rotation but has different surface properties, then these two spheres will have different rotational index. Only we can know that these four variables, we can count them from each other if we know two of them. Probably it exists a formula that can describe this balance with wavelengths as well, but this is out of my knowledge. For key numbers, I show you these three numbers. 394, almost 94 Kelvin, is the maximum value of the temperature if the irradiation is 1361 watt per square meters. And as the standard temperature model is valid, so at the night time it would be zero radiation. And this means that if the irradiation equals with the value I show you, and the temperature we measure like this, then there is no performance for the reflection of the shortwave radiation from the surface. I showed you the temperature value of the isotherm model, which is 278 degrees of Kelvin, which is 5 degrees of Celsius. And I showed you the nighttime temperatures. The first dot, if we divide the x-axis to 50 pieces, then the first piece would be with these values. So if we think that the moon is very close to the standard temperature model because it's rotating very slow, then we will expect low temperatures for the night. We can say that if the sphere is in balance with the radiation, depending on the rotational index, we will see different temperatures on the surface. And now we arrived to Moon. The Lunar Reconnaissance Orbiter is equipped with several instruments. One of these is the Diviner Lunar Radiometer experiment, which aims to map the whole surface of Moon regard to temperatures. I will refer to the mission as LRO or spacecraft, and I will refer to the instrument as Diviner. After 5 years of measurements, the scientific group reported values from the surface, as you can see. The first good news is that they agreed with Dr. Lawson. So the temperature dispersing rule from the subsolar point to the pole can be described with this function. At the first glance, we can see that during the night the surface is cooling, and during the day seems that is very close to the equilibrium. 12 hours later, the subsolar point will be moved along the equator, and we can read in this article that in the morning and in the afternoon side, there's very little temperature difference. So at 8 a.m. and at 4 p.m., the temperature difference is only 1 Kelvin. 8 a.m. and 4 p.m. is at incident angle of 60 degrees. So we can say that the temperature on Moon we can describe of our curiosity of a latitude and the local time, what is on the clock on the Moon. The scientists reported the noontime temperatures and the midnight time temperatures, and as you can see, every latitude seems isotherm. So during the day there is probably equilibrium, and during the night there is cooling. So these two different processes needs different explanation. So I will continue with the day side, and I will get back to the night side later. The first thing that we can read in this article, that the mean zona noontime temperatures can be higher than we counted in the slow rotational model and at the standard temperature model, which is very strange. We can read in this article also that the daytime temperatures are equilibrated nearly with the solar flux, which for me looks very strange, because from 8 a.m. to 4 p.m., which is almost 10 Earth day time, we can see that from 8 a.m. till noon, the temperature rises 63 degrees, and from noon till 4 p.m. the temperature decreases 62 degrees. So we can say that for 10 Earth day time, the temperature can be described as the function of the temperature dispersing rule from the subsolar point to the pole. But we can say that in between 0 and 60 incident angle degrees, this function works pretty good to east or to west. So we can say that the half side of the day side is exactly in equilibrium with something coming from the sun. So I think the nearly equilibrium is not enough for the explanation. In the next episode, I will introduce the diviner instrument to you, and I will chase for the subsolar temperature on the moon. Be well, and don't forget, the sun will rise tomorrow morning for sure.